So how do you stop SYN flooding attacks? As always, we can throw in our favorite defense of over-provisioning, give the server tons of memory so that it can call malloc on 10,000 connections and still have enough left over for other users. That could be one solution. Another possible solution is to try and filter packets so that the SYN flooding attack packets are stopped, but the legitimate packets are allowed through. But that's pretty tricky because it's hard to tell whether a SYN packet is legitimate or part of an attack. If you think about an attacker SYN packet, it has the SYN flag and a random number. If you think about a legitimate SYN packet as part of a legitimate user's connection, it has the SYN flag and a random number. How do I tell these two apart? It can be really tricky to tell which of these packets is from the attacker and which is from a user because the connection just started. There's no other information to use to deduce where the packet is coming from. So filtering can be tricky because we're doing this so early in the connection. So a more robust defense against SYN flooding is a custom-built defense just for this attack called SYN cookies. And here, the idea is to flip the table around. So right now, the attacker has the advantage because they get to go first, forcing the server to store a bunch of state right here without the attacker having to store state. So the attacker doesn't have to go first. They can make the server go first, and that introduces the asymmetry to make the attack possible. So what if we turn the tables and the server said, I'm not going first. I'm going to make you go first. You need to store state first before I agree to call malloc and create my own memory. So this way, we're reversing the asymmetry, and we're forcing the client to store state as well. So this is what it might look like. We're going to turn the tables and reverse and make the client do all the hard work instead. So here's what it might look like conceptually, and then we'll talk about how to implement it. As we said, in standard TCP, the client at this point doesn't have to call malloc yet. They can first send the SYN packet, and the server must call malloc first to allocate some memory. So that's what normal TCP would look like. But what if the server got clever and the server said, this is too early. If I call malloc right here, I am making myself vulnerable to SYN flooding. So I don't want to call malloc right here. I want to call malloc later after the client does it first. So I want to somehow tell the client, you need to go first, and I'll call malloc later to avoid that SYN flooding asymmetry attack. However, the server still has some things they need to remember at this point. For example, the server better know the SYN number that the client sent. Remember that the client has to say their initial starting number, and the server has to remember it so that later in the connection, the server can use that number to see what packets are being sent. So the server does still have to remember things. It can't just remember nothing. For example, it's got to remember that sequence number. It might have to remember who the client is. It might have to remember what port numbers they're using. So the server does have some non-trivial things they have to remember, but they don't want to call malloc right now because that would leave them open to attacks. So instead, the server is going to play a trick. The server is going to take all the things they have to remember, like a sequence number or the port numbers that are being used. They take all of the information that they otherwise would have stored in malloc space, and they just put it in the SYN ACK packet. So here's all the stuff that they should have stored as the server, and the server just sends it back to the client and says, I'm not going to call malloc yet. You might be an attacker. So I'm going to send all this stuff back to you and make you remember it. And if you're a legitimate client, then you'll send that back to me as part of the final message in the handshake. And only now does the server agree to call malloc and start the connection legitimately. So now, who has to store this state? The client has to store it. This client now has to call malloc to remember the state, write it down somewhere when they receive the packet, and then send it back as part of the ACK packet. So we've turned the tables. Instead of the server calling malloc to store state here, the server throws all the state into the SYN ACK packet, sends it back to the client, forces the client to do all the hard work storing it, and then the client sends it back if they're a real client doing a real TCP connection. So now, even if we try to do SYN flooding as an attacker, you can send 10,000 SYN packets, but the server is not going to call malloc at all as a response to those 10,000 SYN packets, so you're not wasting their memory at all. If the attacker wants to cause the server to call malloc 10,000 times, the server is going to send back 10,000 different syntax with 10,000 different state values that the server otherwise would have stored. And now the burden is on the client or the attacker to store those 10,000 values and send them all back one by one for the server to actually call malloc again. So you can still overwhelm the server, but the asymmetry is gone. We can no longer have the attacker send just a little bit of data and overwhelm the server. Now the client has to do the same amount of memory allocation as the server, and the asymmetry is gone. So this is a defense against SYN flooding.